Hello, everyone. Good morning. Welcome to this session on using large language models and foundation models with ArcGIS. And for those of you joining on the live stream, welcome. And for those from the future as well watching the recording, this is 2025. So hello. So I'm Rohit Singh. I'm the development lead on the geospatial AI technology in ArcGIS. And joining me is Karthik Dutt. So Karthik, please go ahead.
Hi everyone. My name is Karthik Dutt. I work as a data scientist, mainly on adding GeoAI features in tabular data text to ArcGIS.
Okay, thank you. Please do share your feedback. It's very valuable for us. So just wanted to remind you about this. So let's get started. So here's an outline of what we'll be going through, so you know what's coming. After a brief introduction to what are LLMs, how do we define a foundation model, and how they work, what makes them different from the prior AI models or the deep learning models. Then we'll break it down into the different data modalities, starting with vision models. So for computer vision and using those with imagery, then talking about large language models, using those with text data, and then multimodal models, combining both vision and language, or foundation models for tabular and time series data. And then finally, we'll have a short summary and end the session. So we've now seen the emergence of large language models and foundation models, starting with the release of ChatGPT that really changed everything about AI, like how it was perceived, how it worked. So broadly, it was fundamentally different from the prior generation of models in the sense that these models are huge compared to the prior generation of models. They are trained on billions and even trillions of parameters. There are many layers of neural networks, and they are really huge in size. They are also trained on internet scale data. So it has built an internal understanding of the world. You don't need to teach it specific things. It already comes with some knowledge that is acquired. And then it started with language, but now we have also seen all the LLMs are starting to integrate other data modalities like vision and speech and so on, even video these days. And for the first time, it seemed like these models are showing sparks of intelligence, what we typically have only associated with humans so far. And especially now with the reasoning models, it's becoming more and more apparent, like the capabilities are really compelling. They understand and generate human-like text and even images. They can be prompted using simple English phrases to perform tasks, and they can respond in English and, of course, other languages as well. And what makes them fundamentally different from the prior way of using the deep learning models is that the same model could be applied to many downstream tasks just by simply prompting them in many cases. We don't need to fine-tune the model weights to be able to teach it a new skill. We could just give it a prompt or give it a few examples, and it'll be instructed to follow our instructions. Foundation models are a little broader terminology. So this is broader than just large language models. And primarily, it's three things that define what a foundation model is. They are trained on broad data. So the data is diverse. It's again, internet scale data. And they can be adapted or perform many different kinds of tasks. The same model can do many tasks. So that's how it's different from very task-specific models like detecting trees or extracting building footprints or classifying land cover. Here, the same model can easily be made to do multiple different kinds of tasks. And the third thing that's not shown pictorially in the slide, but is emerging, is there are the size of the model. Typically, it'll be above 1 billion parameters. And they may have other thresholds, but certain government agencies have said, okay, if it's more than 1 billion parameters, then it's a foundation model. I want to talk about how the technology has evolved, because these are the building blocks of these foundation models. You'll typically find that they use the transformer architecture, which came out in 2017 as a way for language models, but it's finding its application for not just language, but all kind of data modalities now. And it's been described as a magnificent neural network architecture, so an algorithmic improvement over the prior generation. The next building block is training these models using what's known as a self-supervised way. Earlier, we always trained models on labeled data. So given the input image, it's a cat, this image is a dog. Well, it's hard to create those data sets to train models, because at the end of the day, it's a human labeling that. So the other shift is we just give it raw text, and maybe it predicts, we hide a phrase or a word in the text, and we have the model predict that. Or we give it an image and mask out parts of that image, and the model is supposed to fill in the blanks. So what this allows us to do is there's no more need to label the data. It can be trained on raw internet data, and that really helps the model. As these models become huge in size, they need that much more data to train, right? So it allows for larger scale model training. And this is still the pre-training phase. These models are trained over several phases. So the pre-training is done on the labeled data, and then it could be instruction tuned to follow, questions, give answers. So that's done through more of a traditional way, and now in emerging ways using reinforcement learning. And then the third building block is the sheer scale of these models. So what this image is showing is the scaling laws for these language models. What was discovered is, as we increase the compute size, the training, we keep continuing training for longer. As we increase the data size, as we increase the number of parameters of these models, as they keep becoming bigger, the error or the loss just keeps going down, doesn't seem to have any inflection point. So that's what really drove this race towards who has the biggest model. And what we've seen is that the larger models are indeed much more powerful than the smaller models. Now we'll talk about, dive into how do you use them, how does it apply to our work in GIS, and starting with vision models. So, like I said, the transformer architecture also plays a fundamental role in the vision models. The earlier generation of models were built on ResNet architecture, or the convolutional neural network architecture, which for a very long time seemed to be the only way to train these models. But now, with the emergence of a vision transformer, we can take an image, just like a paragraph can be tokenized into words, the image could be broken down into patches and sent through that transformer architecture. So, the architecture is the same, whether it's a language model or it's a vision model, and it's incredible that this architecture allows us to take advantage of larger model sizes, more training data, and the scalable training. And coming to the specific vision models that there are, I'd like to break it down into two categories. It started with general purpose computer vision models. So you might have heard of Meta's segment anything model. That's perhaps one of the first foundation models for computer vision. And then there are other models that came, like segment anything lets you do a pixel classification or a segmentation of any object, not specific objects. Like you're not segmenting land cover alone or finding, segmenting trees alone. It could be anything. And similarly, grounding Dino, we'll talk about that. That was another general purpose open set object detector. But what we've seen emerge recently is that for the geospatial community, for the remote sensing community, we've seen the emergence of remote sensing foundation models. So Prithvi from IBM and NASA is among the first such model that was trained on Sentinel and Landsat imagery. Now we are seeing multimodal and multi-scale, multi-temporal remote sensing foundation models like Dynamic One for All or CLAY. And these have been trained on Sentinel, Landsat, NAPE, Lens, many kinds of imagery, including these days even the SAR data. So these are also coming to ArcGIS. You do need to fine-tune these for the computer vision tasks. So we are not yet able to prompt the purely computer vision models using, like giving it an example that, okay, this is one building and find more of such buildings. That's a very recent, recently new papers are coming out in that. It's an emerging area. But so far, these remote sensing foundation models need to be fine-tuned for your task-specific thing, like whether it's crop classification or flood delineation, and so on. So let's see about specific models now. So starting with the SAM, or the segment anything model, it's the first foundation vision model from Meta. You can see on the right that how the SA 1 billion data set, that's what was used to train SAM, how it dwarfed all the prior data sets used to train these models. So a lot of trained on 1 billion masks and 11 million images. And it can be prompted using points or boxes. It only works with RGB imagery. So let's see something about the SAM model. So I've got a story map here. And here are some examples. Basically, if you've got some objects over a more or less textured or a plain background, you could use the SAM model and it'll segment out those. So here are cargo ships. These are like center pivot models. The same model can segment distinct objects from their background. So earlier we needed task-specific models for each of these. These are land parcels even. But where it breaks down is this has no notion of what it is segmenting. As you can see, the trees, parts of the road, houses, everything has been segmented. So it's only useful where you've got distinct objects over a plain background. That's where it's more useful. Okay, so that was SAM. We'll come to the tech SAM later, what this talks about. So SAM can actually be prompted using points or bounding boxes. So if we give it a bounding box, or we pair it with an object detection model, then we can have SAM segment that model. So this is pictorially a representation of that. So let's say we already have a model to detect trees. And by detection, we mean we only get the bounding boxes of the trees. Now, if we take these bounding boxes and feed them into SAM, it'll precisely segment those out, give us their precise geometry. So we'll know the sizes or the canopy dimensions through this. So what this allows us to do is we can actually package any object detection model with SAM and turn that object detection model into an object segmentation model. So how this helps you is, one is we've used this approach to create newer variants of our models. You briefly saw the tree segmentation there. There's some internet issue with loading this. Let me try again. But on the Living Atlas, now we've got models which do segmentation of certain objects. So whether it's trees or swimming pools, that allows us to do this. Additionally, you can also do this through the extract features tool and extract features using deep learning. That's a tool in the GeoAI toolbox. You could take any object detection model, and there's a post-processing option to create these segments using the boxes as prompts. Using SAM is very easy. So this one is showing the grounded SAM. This is showing like how SAM could be prompted using text prompts. So it's coming, we've given it an example of circle or object. So if we take a model that can take, a prompt and just finds its bounding box, we could then feed it into SAM and get the segments out. So that's how we've created the text SAM model. So here we could say you only detect the tree, the aircraft or the ships, and it won't then detect the other types. So this is with cars. Even you can go finer grain, just find the yellow cars. So this was very interesting that this is possible. But what if you cannot, you want a task-specific model? Let's say you want to detect the buildings and it's not doing a good job. We now give you the ability to fine-tune SAM itself using what's known as a low-rank adaptation approach. Typically, SAM is a very heavy model, and training it would need a lot of compute resources. But by just training these so-called LoRA layers shown in the bottom here in this image, we can adapt SAM to perform task-specific fine-tuning on everyday GPUs that you have. And this has been integrated with ArcGIS. You can now fine-tune SAM model on any task. So this is doing it for the building footprint extraction. So we just spoke about the SAM LoRA approach. Because it's quick to train and low GPU requirements are there, it is environmentally friendly. You don't burn so much, carbon credits in training your model. And what's interesting is that we've done it in a way that it also works with multispectral imagery. Typically, SAM can only, it only works with RGB imagery. It's a general purpose model. But with this integration, you could have multispectral imagery and fine-tune SAM. Then coming to the remote sensing foundation models. So Prithvi from IBM and NASA was the first such model, although its resolution is a little low compared to the newer models at 30 meter spatial resolution. There are new versions of Prithvi coming out and being worked on. There's also a weather and climate variant trained on weather data. And this is used for pixel classification or segmentation tasks. And they've provided 3 variants of Prithvi, one for crop classification, one for burn scars that you saw in the plenary on Tuesday, and then one for flood mapping. But you can actually adapt it for your specific tasks, just like IBM and NASA did it for crops, burn scars, and flood mapping, we give you the ability to fine-tune Prithvi. So let me show that to you, how you do that. So here's the Prithvi burn scar segmentation model on Living Atlas. Here you can see it being applied to detect the burn scars. Now on each model item page, it shows how you can use the model and also how you can fine-tune the model. So by following this link to the guide, it tells about how you prepare the training data for your task-specific needs. And then using a low-code approach, using the ArcGIS Learn API, you can take your exported data and these like typical 5 lines to train a model using the ArcGIS Learn API. It's a part of our Python API that lets you perform geospatial deep learning. That's how you can fine-tune the Prithvi model on your data. Then it goes beyond just imagery. So you've got weather data, and you want to perform climate forecasting. So Climax is one such model from Microsoft for weather and climate forecasting. It helps you do climate downscaling and weather forecasting. And we allow you in ArcGIS to fine-tune it on your own weather data. So this is just an example of what we tried with it. You may know that sea surface temperature, it's related to the health of coral reefs. So if the temperature rises for only a short time, the reefs can recover, but if it's sustained high temperatures over a long period, then the reefs suffer and get bleached. So we tried it on one such data set. What we found is that, well, the same thing can be done using the temporal analysis tools in ArcGIS, and they are modeling simpler relationships, harmonic relationships, mathematical relationships. But a model with these millions and billions of parameters can handle or understand more complex phenomena. It can analyze complex patterns for these predictions like sea surface temperature. So here in the green, is it the blue color? This line, that's showing the ground truth. And you can see how closely the forecasts from the Climax model, shown in orange, are following it. Whereas a trend analysis tool will only model a harmonic relationship. So we were also surprised by it that how well this model works. This graph is showing the error rates. So the error for Climax is much lesser than trying to model it using the simpler techniques, the algorithmic approaches. Now we will switch to the section on large language models, and I'll hand it over to Karthik.
Thanks, Rohit. So we'll first start by talking a little bit about how the evolution of the support to the large language model from within ArcGIS has happened over a course of time. So it all started with this seminal paper on transformers, which came out in 2017. The paper itself, titled as Attention is All You Need, introduced the concept and the architecture of transformers. And since then, all the large language models that are being built are based out of this particular architecture. So the very first models which were based out of the transformer architectures were the BERT models from Google and GPT-1. These models had close to about 100 million parameters, which was large at that point of time, but it's not now, because all of these models which are getting released now are close to about 100 billion, definitely more than 100 billion, close to 1,000 billion parameters. So these were the first large language models which were released in 2018. And since then, these models have progressed and becoming larger and larger. And until 2022, when ChatGPT was released, which had more than about 100 billion parameters, and it was built based on GPT 3.5. And 2022 was also the year when we had our GeoAI toolbox, which released, and these toolboxes had the support to perform text analysis tasks by making use of all of these large language models. In fact, much prior to that, starting from 2020 onwards, we had the same support available in the ArcGIS API for Python. So since 2022 onwards, we have realized, in fact, we all know how fast the progress of these large language models have been. There have been larger models and the open source variants of these models and the proprietary variants of these models. And we have been supporting, we have established the support to from within the ArcGIS tools and the API to access some of these models. So, but now we do realize that we cannot catch up with the pace at which the models are being released, and we want to offer that flexibility and the support to connect to these large language models from your by writing the deep learning packages yourself. In the next slide, I'll talk a little bit more about what these deep learning packages are, how you can write them, and we call this feature as model extensibility. So prior to 2022, when we didn't have such large language models, when we just had the GPT-1s and the 2s, the users were required to train their own models for specific tasks by making use of the tools which are available within the GeoAI toolbox. We had the tools available for text classification, entity recognition, text transformation, and you were required to train the models, and you were required to create your own sample data in order to train these models. Since 2022, because of the generalizability of all the newer versions of these large language models, it's no longer required in many of the cases to train your own data in order to perform a certain specific task. You could just directly feed in your data to these large language model and ask it to perform, using prompts, you can ask it to perform a certain task, and they will be able to do that for you. So prior to 2022, when you were training these models, you would end up with a deep learning package, which you would use in order to get the inference from these trained models on your new or the test data. After this, as I told that there was no need to train this model, we started providing pre-trained models or pre-trained DLPKs, specifically for text analysis tasks. Like we had a deep learning package for Mistral. So you could just download the Mistral DLPK and run it on your machine, pass your data to the model, and prompt it to perform the required task for you. And from then onwards, as I told, since there are so many new models that are being released, we are not able to catch up with the pace. We are not able to provide the deep learning packages for each one of those. So we are now opening up that opportunity to create those deep learning packages as users yourselves. So now, depending on what model you want to connect to, whether it is cloud or whether it is on-prem, whether it is a commercial model or whether it's an open source model, you can write your own DLPKs and you can actually connect to those models, perform the tasks which you want to, and get the results back into ArcGIS. In the demo which we are going to talk about now, we'll see how you can create your own deep learning packages. In this demo, I have a table of about 400 records. Each of these records is a natural disaster event that occurred across in United States over the last 3 or 4 years. And each of this record has details about where the damage or where the disaster occurred and what was the category of the disaster, how many people were impacted due to this disaster, what was the monetary amount associated with it, all of this. And if you notice, all of this information is present as unstructured text. Now, let's say I want to convert this unstructured text into a much more structured format. So this task is called entity extraction, named entity extraction. To do this, I'm going to make use of this tool, which is called the Process Text Using AI Model tool. This tool will be released in the next couple of months with the next release of ArcGIS Pro. This tool can perform a range of tasks. It can perform text classification, entity extraction, transformation, any of the other tasks which you want the large language models to perform. So this particular tool, I've passed in my data as input. I've specified the column where I have my unstructured text. And I'm pointing it to a DLPK or the EMD file, which I just created for this purpose. It's not a pre-trained deep learning package, but this is just a customized one, just in order to handle this use case. And now let's see how this deep learning package looks like, how you can create one of these. Deep learning package is just a zip file containing these two files. One of those is a Esri model definition file. The other one is a Python file, which contains most of your logic on how to connect and get the results from your large language models. The EMD file looks like this. It is just a JSON structure which has the inference function. You can specify the file where you are having the core logic on accessing or on how to access the LLM and retrieving the results. If you were to write your own DLPK, you might just have to modify the file name here and keep the model type as process text. Now let's go to the other file. In this other file, I just have this single class. So let's talk about what this class does. So this class has 5 different methods. The first of which is the init method, where I'm just describing what this class is for and what's the name of this particular class. Next, I'm having an initialize method. Here, I don't have anything. If you have a model which is hosted on your own premise or your own local desktop, you can provide the details on how to access that in this particular method. The next one is the get parameter info. Here, I'm describing what are the parameters which I need to display on my UI. Here, I have 2 parameters, the prompt and the connection file path. So if I go back to the UI here, you see that the same 2 parameters appear here. And the value which I entered here, this is the default value which comes in the prompt parameter. So it is up to you to define what parameters you want to define for your use case. You can specify, you can either add parameters or remove parameters and customize your UI for your specific task. So now going back, the next one is the get configuration method. Here I'm extracting all the details that were passed in my UI. For example, here in this case, what I'm doing is I'm connecting to the connection file, and I'm extracting all the connection parameters that are required to connect to my large language model. Now let's talk a little bit about what this connection file is. Right. So the connection file itself is a JSON structure. It holds all the required details in order to connect to your large language model. It could be your cloud-based model, or it could be on-prem model, open source model, or anything. So how do you create this connection file? So to create your connection file, we have built a new tool, which is also will be released with Pro 3.5. Here you can specify the name of the connection file and the path where you want to save it. And you can also choose the service provider, the AI service provider, where your large language model is hosted. So we have currently support for AWS, Anthropic, Azure, Hugging Face, OpenAI, and Google. And if your service provider, if your large language model is not on any of these, or if it's just on your on-prem machine, you can choose the others and pass in the required connection parameters. So let's say I choose OpenAI, and here I'm asked to provide my model ID and the API key. The API key itself is hidden, so while you enter it, and all of these details that you enter here will be written to a JSON structure, JSON file, which we have mentioned here. The secret parameter itself will not be mentioned and will not be written to the file, but it will be saved in your Windows Credential Manager securely. Now coming back to the first tool, So we now know how to create our connection file. So I'll pass the path where I have saved my connection file here and run the tool. So coming back to the code here. So here, that's what I'm doing. I'm just extracting all the required connection parameters in this method. And in the next one, I'm actually connecting to the model itself by using the requests. I'm connecting to OpenAI, passing all the required parameters. I'm reading the input text, which was present in my feature class one by one, passing that information, getting the response back from the large language model, converting it to a structure which I want. In this case, I'm converting it to a JSON structure and writing it back to my feature class. So when I run the tool, this is what the output looks like. So this is where I have my input. And these are the entities which I've extracted. I've extracted the event, the type of event, the year, the origin, location, fatalities, and cost, and so on. All of this information was extracted, was provided to me by the large language model. I have not trained any model here. I've just utilized the inherent power of the large language models to extract all of these entities. Now let's say I want to take this one step further. So I have all the locations here. I want to take it to a map. So in order to do that, you can also provide the geocoding service URL here. You can provide that, and I can, when I run it, I can bring them up onto a map. And if I click on any of these feature classes or the features, you will see that it gets displayed here. So this is the input, and these are my entities that were extracted. So imagine the scenario. A couple of months down the lane, you have, let's say, GPT-5 coming up, right? So, and if you have the access to that particular model, or to any other model for that matter, which is much more powerful than what we have right now. So if you have the access to that model, the very next day, you can create your own deep learning package and bring in all the power of that model to your ArcGIS and to perform your task. So that's how powerful this new feature could be. So the next thing which I want to talk about is a little bit about the assistants. So we have been discussing about how powerful these large language models are, but they cannot perform all of the tasks that we want to at this point of time. For example, if I ask it to find the nearest route from Central Park, New York to the nearest library, I don't think it will be able to perform this. So that's where assistants come in handy. So assistants are entities which takes in user input. It has its own memory. It also has certain tools or scripts which are available within its arsenal, and using which it can connect to the large language model and can perform tasks which a LLM cannot do by itself. So let's talk a little bit about what these tools or scripts are. So tools are just, you can consider them as methods with a description on what task it performs and what are the parameter it takes, what input parameter it takes, what are the output parameters it provides. It is just a method which is let's say an encapsulation, or which can written on top of your any of the existing ArcPy tools. So let's say we have an ArcPy tool for geocoding or routing or nearby search. So we write a wrapper around it and provide description on what it does, and that's a tool for you. So you can use any of these frameworks which are available for building these tools, like LangChain. So once you build these tools, you make it available to the assistant. Now, when you ask this question, what the assistant will do is it will take your query, it will get the information on what are the tools available for it to perform this task, and take all of this information and take it to the large language model. Now, the large language model, because of its reasoning abilities, what it can do is it will be able to orchestrate a plan on how exactly to perform the task. It will be able to understand the intent of the user. It will be able to gather all the required input parameters from the user's input. And it will also be able to orchestrate a plan that, okay, we need to call tool 1 first, tool 3 next, and tool 2 at the end. So it will be able to do all this orchestration, and it will be able to send the response back to send this orchestration plan back to the assistant. The assistant itself will be taking this orchestration plan and reading that, and it will be able to perform this task. So that's how the assistants work. So if you combine the power of, let's say, ArcPy or any other methods in ArcGIS API for Python, and combine that with the large language models, you could build your own tools in order to perform more complex tasks, which our large language models currently cannot do. So with that, I will hand it over back to Rohit now, who will be taking us through the rest of the content.
Thank you, Karthik. So, the example Karthik showed about building assistants. So both in ArcGIS Pro, there's the skill framework, and the skill framework in ArcGIS Enterprise and Online. They have the ability to create custom skills, and that's how you would integrate this pattern in ArcGIS. So the Pro Assistant is in beta at Pro 3.5, and the AI skill framework will be in beta later this year. The example that Linda showed you at the plenary, where she was speaking verbally with an LLM, was using this approach that Karthik just spoke about. Now let's talk about vision language models, combining vision with language. So starting from the simpler to the more capable or sophisticated models, it started with open set object detection models. Basically, open set means you just give it any phrase or word, and it'll detect that object in the image in form of a bounding box. Then you can, like I said, you could feed it into SAM and get a segmentation of that. So that's how we implemented text SAM. But that's for objects, when you want to segment objects. But not everything is an object. It doesn't have a well-defined boundary. It could be amorphous, like a lake or a river. It may be different sizes. So that's where an object detection approach won't work. You need to segment that object. So for that, there's another vision language model called ClipSeg that we've leveraged to create the prompt-based segmentation model. You could write out what you're looking for and segment that object. Then there's a zero-shot classifier, and I'll talk about that, followed by the more powerful models like GPT-4o and Llama being used to classify objects in imagery as well as ask questions of imagery using the image interrogation and the vision language context-based classification models. So let's quickly see their capabilities visually. So this is like the grounding dino model. You give it any prompt and it'll segment out, or rather detect that object in form of a bounding box. So this is using swimming pools, but you could use it for other objects. This is detecting the aircraft in that aircraft graveyard. We saw the application of grounding Dino and combining it with SAM through text SAM. I showed you a few examples. So this is what text SAM does. But it detects things, not stuff. That's just a computer vision phrase used, right? When you're finding precise objects with a defined shape, it's objects. But if it's like everything else, or those things that don't have a precise shape, that's the stuff. So that's where the segmentation model would work. Then there's CLIP, the contrastive language imagery models. These are basically let you align images with text. So how we apply them is it's zero-shot classification. Zero-shot meaning you don't train it, you just give it the problem. So given an image, you could say, is it a congestion or a collision? And it would say it's congestion. So you just provided the labels, the possible labels, and it'll assign the closest label to what's in the imagery. It'll align the vision or the image with your text labels, and whatever has the most similarity, that will be the assigned label. So it could be used for classifying images without training at all. Now coming to the prompt-based segmentation. You could give it a prompt like, I want to detect water. I mean, I recall maybe a couple years ago, somebody wanted to, find, his task was to digitize the rivers. And I told him how he could train a model for that. Well, fast forward 2 years, now we have a model. You could just prompt it with river or water, and it'll segment it out for you. That's what ClipSeg or the prompt-based segmentation model does. What's interesting is that your prompt could not just be an text, it could even be an image. So for example, in this image on the left, we gave this photograph of a car which doesn't even exist in this image as the prompt. And it's able to create this probability raster highlighting where this object or concept appears in the input image. And then we could threshold it and just find those cars. So how do we use it in ArcGIS? Well, we could, this is an example from hurricanes, Hurricane Helene and Milton, where we gave it the prompt debris piles, and it was able to detect the debris piles and segment them out. Now we come to vision, language, context-based classification models that I showed a demo of in the plenary. Basically, even today, you could take this image, give it to GPT, and give it a prompt that I want you to classify it and say what kind of category it has, like no damage, minor damage, or heavy damage, or the building is missing or destroyed, and also give a reason. GPT or these vision language models are able to do that. But how do you apply this to a GIS system? Right? We've got layers of GIS data, we've got layers of building footprints, and by this integration, what we do is we go to each GIS feature, clip out the image at that part, send it to that language model, vision language model, and have it provide the classification and the reasoning. And the results come back as GIS layers. So this is a hurricane scenario where the model is able to tell what kind of damage the buildings incurred. And you can see it's quite accurate. It even gave, like, we didn't initially give the prompt building missing or destroyed. It suggested that as a prompt, rather a label. So you can choose to just have the model, use your labels or even come up with new labels. There's another scenario from Hurricane Milton. It was able to find which of these buildings were damaged, which were intact. So very briefly, I wanted to show you these results. This is the scenario we just saw. Here we pointed to the Hurricane Milton imagery, provided the layer of buildings, picked the vision language classification model, and I've given it what classes to categorize the damage under, and some context about what the model is looking at. Here we can tell the model whether to just use the labels I've provided or a more loose classification where it could give its own, hallucinate new ones. This is using the AI connection file that Karthik spoke about. And then that was for classification, but you can use this approach or another model called image interrogation to ask any questions of images and have it answer, like, what do you see in this image? So here it's replied that it sees an aerial view of a marina with many boats docked on the waterfront with large building, that's the San Diego Convention Center and the Marriott Hotel, and a smaller building. And this is about another scenario about an airport. But there's also other data modalities. A lot of work you deal with feature, tabular, and time series data. And there are these foundation models appearing or emerging for these tasks as well. So there's the TAB PFN foundation model by Prior Labs that can just, without any training on your tabular data, it can solve classification problems. And this has been integrated with the upcoming release of the Python API. Then here are some examples of time series forecasting models, like Times FM and Chronos. And you can see how the original and the projected data is matching so well without even training, zero-shot performance. And these models can be integrated with the GeoAI tools for time series forecasting using a similar approach that Karthik showed. You could create a Python time series function just like he created a Python NLP function. So coming to a summary, we've seen how the AI capabilities, whether we want computer vision or the ability to see or read, in each area of AI, we are seeing the emergence of foundation models, language models, and they are coming to ArcGIS. And here are several examples of the things I showed you. The question might come up like, does this obsolete the task-specific models? No. Task-specific models are pretty good at what they do. And in many cases, they are more accurate than the general purpose foundation models. Also, as of today, we've created task-specific models for remote sensing imagery, but we don't have enough general purpose models on remote sensing imagery. They are just trained on RGB imagery. Another consideration is that using the task-specific models has lesser GPU memory requirements. One shift is, well, you don't always need to fine-tune a model. You can first try a prompting approach, see if it works. If it doesn't, then try to fine-tune your model. Hallucination does continue to be a problem with LLMs, like it can make up categories, and that's where the review is important. AI needs a human in the loop to review, and because we are solving very critical problems for people, we need to have that human oversight. And these models, because they are trained on internet scale data, some of those biases carry over to these models. So we have to be aware of that and see where bias may have crept in and address that. So that was what we wanted to share. We do have 5-6 minutes for question and answers. If you'd like to ask any questions, you can raise your hands. We'll be happy to answer it. And on the live stream as well, if you have any questions, you can continue posting them. Thank you. Yes, there's a question here.
Efficient fine-tuning techniques for adaptation. Why only LoRA is chosen, or you can integrate others like adapters?
So the question is that there are several parameter efficient techniques or PEF techniques for fine-tuning these large models, and why have we only chosen the LoRA technique? Yes, so good question, very technical question. I love these technical questions. As the technology evolves, we keep pace with it, and you will see more such techniques being adopted. So for our language models, we are already experimenting with other such techniques, other PEF techniques, like quantization, for example. And you will see more of these coming in. It's just how things get merged into ArcGIS. Yes.
I saw the AI functionality of ArcGIS Pro. So is there anything coming up for ArcGIS Enterprise and any AI functionality sitting on top of Experience Builder or any web apps?
Okay, great question. So the question is that in our demos, we showed examples using ArcGIS Pro, but is something coming for ArcGIS Online and Enterprise and in the apps like Experience Builder? Yes, in fact, it's already there. So all of these AI capabilities we showed, there are these raster analytics capabilities in the image server, in enterprise and ArcGIS image in online. They are available through REST APIs, and you could use these models both in all pillar products like Pro, Enterprise, and Online. And because they are accessible through REST APIs, you could call them through the apps like Experience Builder. The text capabilities, the tools are currently in Pro, and as part of the AI framework, it's something that there's an R&D effort ongoing, and they will also be coming to online and enterprise. Yes. All right, thank you very much. We'll be around, so if you have any questions, you can come by and ask us in private as well. And thank you to the audience watching us live.